All right, in this video, we're going to take it one more step, and instead of just finding the z-scores, we're going to learn how to find the x-values. So z-scores and x-values are completely related. Just remember that your z-score is when we transform that x-value into the standard curve. So you make the mean 0, you make the standard deviation 1. Your x-values refer to the raw data points, right? So if you're talking about heights, it would actually be the heights of the people, or if you were talking about like survey data, it'd be the answers of the survey. So it's the actual data values that have not been transferred to z-scores. So they give you the same distribution, it's just that it depends on what you're looking for. So here we're going to be able to transform an x value. Well, I should say we transform before an x value to a z-score, right? So in a previous section, we looked at how to create a z-score by using this formula here. And we can actually rearrange this formula to work backwards. So this way we can go from a z-score to an x value. So I'm just going to show you how to do that real quick. So let's say I have z equals this x minus the mean over sigma. So to change this around, what we do first is we multiply both sides by sigma. And that gives us sigma z is equal to x minus the mean. And then what I can do to get x by itself is I can add that mean to both sides. So I have a final formula that looks like this, and usually we rearrange it. We tend to like the solve for value on the left. So the formula that you can use, that you don't really need to know how to solve this, but the formula that you need to be able to use in case you want to go from a z-score back to an x value is this one right here. So let me just make a little note here. So if you're going from an x value to a z-score, which we've done in previous sections, then you're looking at the formula z equals x minus the mean over sigma. If you're going from a z-score to an x value, then we're going to use this new formula, the mean plus z times sigma. So again, if they're touching there, you do have multiplication. So those are two formulas you want to keep in mind as you go back and forth. So a veterinarian records the weights of cats treated at a clinic, and the weights are normally distributed, so we have that bell curve. The mean is 9 pounds and the standard deviation is 2 pounds. So what I know for all these cases is our mean is 9 and our standard deviation is 2. And then we want to find the weight x corresponding to each z-score. So remember, your x values refer to the true units, whatever the information was about. So z-scores are always standardized. Mean is always 0. Standard deviation is always 1. They don't really have units. So your x values are the raw data. So if we're studying weights here, the x values are the actual weights instead. So here I have my first z-score. And again, because I want to go to the x values, I'm going to use this formula. And what I'm going to do is I plug in the mean, which is 9 in this case. I have the z-score, which is 1.6, and I have my standard deviation of 2. And then I'm just going to take out my calculator here. So let me do it kind of for you on the screen. So I'm going to do that 1.96 times 2 first. So you do want to use your order of operations. This gets done first. You get 3.92, and then I add that with 9, and I get, and that did not work, 3.92 plus 9, excuse me, is 12.92 pounds. Okay, so a z-score of 1.96 would refer to a cat that's almost 13 pounds. Now for the next one, we're going to do the same thing. So again, I'm going to go back and go from the z-score to the x value. So maybe I just want to change between the two forms. So I have 9 plus the negative 0.44 times 2. And again, just be careful. You do have a negative here. So we're adding with negative 0.88. And when you do that, you get 8.12 pounds. So a z-score of negative 0.44 refers to a cat that's a little over 8 pounds. Now, keep in mind, this makes sense because, you know, if you're in z-scores, your mean is 0, right? So your z-scores are negative, and then over here, your z-scores are positive. So when you transfer back to the x values, here our mean is 9. So our values on the left here, so our negative z-scores, second. So a negative z-score is to the left of the mean, right? So if you're transferring to the x value that's over here, it's going to be a value that's smaller than 9, right? Because instead of being your center of 0, your center is 9 here. So it makes sense that a negative z-score would be for a weight that's less than 9 pounds. And a positive z-score, again, you're going over here on the graph, is going to be a weight that's greater than 9 pounds. So you have the same distribution of the same picture. It's just that you're transferring from one form to another. So for this particular case, negative z-scores are going to refer to weights that are less than the center, which are 9 pounds. And positive z-scores are going to refer to weights that are more than the center, which in this case are just 9 pounds. So that's why you see the different weights there. Now, when z equals 0, that's equivalent to the mean here. But in case you're not sure, we can still use that same formula. And our mean is 9 and our z is 0. So again, this piece is just going to cancel out. So your z of 0 is always equivalent to that mean, which is 9 pounds in this case, in the other form. Now, why do we need to know how to go back and forth? Basically, so we can answer probability questions and things like that. So normally, you may have some data and you're trying to figure out what the x value is for a certain probability or certain area cutoff. All right, so let's actually look at some full examples here. All right, so this says scores for the California Peace Officer Standards and Training Test are normally distributed. So again, we have a bell curve. So if you see normally distributed, you have some sort of bell curve there with a mean of 50 and a standard deviation of 10. So before I even do anything, I'm actually just going to draw that picture. So I know I have a bell curve here. I know my mean, which is my center, is the value of 50. And I'm just going to make a note over here that my standard deviation is 10. An agency will only hire applicants with scores in the top 10%. What is the lowest score an applicant can earn and still be eligible to be hired by the agency? So they will only hire those in the top 10%. So again, 50% on the left, 50% on the right. So your top 10% is going to be like over here. Okay. And remember, 10% would be the same as 0.10. So we move that decimal 2 spots to get the decimal version. So we're looking for this cutoff right here. Now it's an X value because I am not in a standard normal distribution, right? Z values are for when the mean is 0 and the standard deviation is 1. If I have anything else, it's an X value. Okay, so my mean is 50, my standard deviation is 10. That's not a standard normal curve, so I'm looking at my X values here. So they want to know what is that cutoff score for the applicant. Now, we can use technology or we can use the table here. So if you're using technology, which is the easiest way to do it, is you're just going to use that same inverse norm function that we used before. So we're going to do it in 1 second, but we're going to do inverse norm. And remember, it's always the area to the left. So even though I know the area to the right of the cutoff mark, I need to actually input the area to the left. So this area over here is 1 minus 0.10 or 0.90. So if I have 10% to the right, I have 90% to the left. So I'm putting in 0.90 here. The next thing you enter is always your mean. Now in this case, my mean is 50. And then the last thing I enter is my standard deviation, which is 10 here. So if you're using the calculator or the app or calculator, whatever one you're using, then there's really no change to the format at all, which makes it really nice and easy. It will spit out that X value for you right away. So I'm just going to hit that second bars button here. So don't forget, it's second bars first. And then I hit inverse norm. My area to the left is 0.90. My mean is 50, and my standard deviation is 10. And it's going to give us that value. So I get X is about 62.8155156. And let's just see, it looks like your book rounded to 1 decimal place, so we'll stick with that. So about a 62.8 would be a minimum cutoff score to be hired in this case. So that is your minimum cutoff score. Now, again, I recommend technology. It's going to be the fastest and easiest way to get those values because technology can output the z-scores if you type the mean of 0 and the standard deviation of 1, or it can output the x values if we just type in the mean and the standard deviation given. So it can give you whatever answer you need, and it makes it really fast. If you're using the table, though, you actually have to find a z-score first. Okay, so if we're going to use that table, the first thing I need to do is find the z-score for the area of 0.90. Okay, so you're still using the area to the left like we did here. But if I'm using the table, my table only has z-scores. It doesn't have x values. So you can only get the z-score first. So let's bring that out. And again, I'm looking at the positive side because I know it's going to be over the 50% mark. So my z is going to be positive here. So if I come here and I look for that 0.90, see if I can find some. Right, so I see 2 right there. Right, and I think last time we ended up doing this already, we rounded to 1.28 here. So if you look here, 0.8997, that's very close. 0.9015, also very close. So you're looking at about 1.28 or 1.29 there for your z value. If you want to err on the side of caution, you can kind of do 1.285 and use that value instead. But you're going to have to estimate. So sometimes with the table, like I said, it doesn't always come out perfect, which can kind of be a pain sometimes. So I'm going to use the 1.28, which we actually found if you on the page before. So we did this 90th percentile already. So I'm going to use that 1.28, which is what your book uses for their estimate there. So I find the z-score first, and then I have to go and change from a z-score to an x value using that formula from the page before. So our x value is equal to the mean plus the z-score times the standard deviation. So our mean here is 50. Our z-score is 1.28 and our standard deviation was 10. So this becomes 50 plus 12.8, which is 62.8. So we do get the same value. Sometimes if you use technology versus the table, you may be very slightly off, by a decimal piece because of rounding errors. So here we had to round the 1.28, right? It wasn't exact when I did my calculation. So sometimes there's a little bit of chance for it to be off. The technology answer is actually always more accurate than the table answer. But they're both good. If you don't want to use technology, you can use the table, but just keep in mind the table only does z-scores. So you get the z-score first, then you change to your x value. Whereas with technology, you can go right to the answer. All right, let's do one more. In a randomly selected sample of women ages 20 to 34, the mean total cholesterol level is 179 milligrams per deciliter with a standard deviation of 38.9 milligrams per deciliter, and assume the total cholesterol levels are normally distributed. So I see normally distributed, so I know I'm going to have some sort of bell curve. I see that the mean is 179. And the standard deviation is 38.9. So again, I'm just going to make a note kind of somewhere off to the side or underneath, doesn't really matter. So you keep in mind that standard deviation. Find the highest total cholesterol level a woman in this 20 to 34 age group can have and still be in the bottom 1%. So bottom 1%, right? So that means we want just 1% to the left, and then everybody else is above that if we're going on the bottom. So something like way over here, right? And again, that 1%, if I move my decimal 2 spots to the left, I'm actually using area or probability of 0.01. So Probabilities, areas, remember they're all interchangeable here. So if I'm using my calculator, the inverse norm, the area to the left is going to be 0.01, the mean is 179, and my standard deviation is 38.9, and that's going to give us this X value that we're looking for here, right? Because we're finding the highest total cholesterol level, so we're looking for the X value. All right, so let's take out our calculator. We do second bars inverse norm, 0.01, 179, and 38.9. And what I get here is that X is about 88.505067. And let's see here. Make sure I typed in everything right. 79 and 38.9. It looks like they're rounding to 2 decimal places. So we'll use 88.51. So just rounding to the second decimal place here. And the reason they're probably rounding to 2 decimal places is because your standard deviation is in 1 decimal place, so you usually use 1 extra. So that's likely why they're using 2 decimal places instead here. So we're looking at about 88.51 milligrams per deciliter for our cutoff value. Now, if you're using the table, again, the first thing I need to do is actually find the z-score, in this case for the area of 0.01. So again, it's on the left here, so I'm going to use my negative z table. Sorry, all this shuffling, kind of a pain. All right, let's see. Here's my z table. I'm looking for 0.01. So I'm kind of seeing it around here. So 0.0099, 0.0102, those are both very close. The 0.0099 is actually a little bit closer, right? So this is negative 2.33 for our z-score. Okay, so I get that from the table, and then I'm going to go ahead and transfer that z-score to the x value here, because I want the actual x value, not the z-score. So I take my formula. My mean is 179, my z-score is negative 2.33, and my standard deviation is 38.9. And I use my calculator here, and what you're going to get is about 88.36. Now, again, this is also correct. I know it's a little bit off from your original answer here. And it's because of rounding error. It's because when we picked that z-score of negative 2.33, it actually wasn't 0.01, it was 0.0099. So you're a little off, but it's still correct. So usually my math lab gives you a little bit of wiggle room, so it should be fine. But if you're having issues, let me know. Technology, though, is actually always the more accurate one. So if you're debating between, or if you don't care which one you use, your technology is actually more accurate than your table. And again, that's because the table is already pre-rounded and not every value is there. So you're kind of estimating or rounding again to get your z-scores. So they're both good, but you do see some discrepancies sometimes between the table and between the technology and its rounding error. So if you can use technology and you like it, it's going to be faster for you, but it's actually going to be more accurate.